If someone told you there was a technology so bizarre, so fundamentally alien to our everyday experience that it behaves like something straight out of science fiction, you'd probably picture spaceships or artificial intelligence, or maybe even time travel. But the strangest and most revolutionary technology we've ever conceived doesn't come from the future. It comes from the quantum realm, a domain where particles blink in and out of existence, teleport from one location to another without crossing the space in between, and hold memories of interactions that defy distance, logic, and sometimes even sanity. It's a world that's invisible to the naked eye, and yet increasingly present in the machines scientists are building right now in labs around the globe. This is not science fiction. This is quantum technology, and it's reshaping everything we thought we knew about information, computation, and the very nature of reality. To understand this strange technology, we first have to admit that the classical world we know, the world of bouncing balls, rolling cars, and orbiting planets, is a kind of illusion. It's a useful approximation, sure, but it's not the deep truth of the universe. At small scales, reality breaks down in ways that are so counterintuitive, so utterly bizarre, that even the most brilliant minds in history have struggled to explain it. We're talking about a world where particles can exist in multiple states at once, where measuring something changes what it is, and where cause and effect blur into an eerie dance of probabilities. The foundation of all this is quantum mechanics, a theory that has been around for more than a century, but has only recently begun to transition from abstract equations on a chalkboard to something engineers can build and manipulate. In this strange framework, even something as familiar as the concept of spin becomes unrecognizable. When we talk about quantum spin, we don't mean something is physically spinning like a top. Instead, it's an intrinsic property, something that defines a particle's behavior, but in a way that defies classical analogy. For an electron, for instance, spin can take only one of two values, up or down, not because it's spinning in a literal direction, but because those are the only two allowable states the universe permits it to have. Try to imagine a coin that's not just showing heads or tails, but somehow exists in both states until you look. That's closer to the truth than anything you can model with ordinary experience. And this strangeness has consequences, profound consequences. Because when you take enough of these quantum rules and start assembling them into systems that can maintain quantum behavior without collapsing back into classical patterns, you begin to unlock a new type of machine. A quantum computer is not just a faster version of your laptop. It's not a more powerful calculator. It's an entirely different beast, built on principles that defy the binary logic of 0 and 1. Where traditional computers store information in bits, simple on or off states, quantum computers use qubits, which can be in a superposition of both on and off simultaneously. And when multiple qubits become entangled, the state of one instantly affects the state of the other, no matter how far apart they are. This is not a metaphor. This is physics. Imagine the implications. A computer that can consider every possible solution to a problem at once, not by brute force, but by leveraging the natural parallelism built into the universe itself. That's the potential quantum computers hold. They're not just fast, they're fundamentally different. But building them is anything but easy. At the heart of every quantum computer is a fragile dance between coherence and chaos. Quantum information is delicate. The slightest vibration, the smallest trace of heat, even a single stray photon can destroy the quantum state of a qubit and collapse it into classical behavior. That's why these machines don't sit on desks. They live inside gigantic dilution refrigerators, towering contraptions filled with layered insulation, vacuum chambers, and cooling systems that bring them to just a fraction of a degree above absolute zero. That's colder than deep space, colder than anywhere naturally found in the universe. And it has to be, because only at these absurdly low temperatures can the circuits used to make qubits enter a regime where quantum effects dominate. These aren't circuits in the normal sense. They're engineered to behave like artificial atoms. You take a simple circuit element, like an inductor and a capacitor, together forming something called an LC oscillator, and you cool it to near absolute zero. At that point, the energy levels in the circuit stop being continuous and instead become quantized. The circuit starts behaving like a quantum system with discrete energy levels, just like an electron orbiting a nucleus. And if you inject just the right amount of energy, say a microwave pulse tuned to a specific frequency, you can drive transitions between these levels. You can flip a qubit from 0 to 1 or create superpositions of both states simultaneously. But to make this work, you need more than just an oscillator. You need nonlinearity. If the energy levels in your artificial atom are evenly spaced, then it's hard to selectively address just one transition without hitting others. This is where a critical piece of technology comes in, the Josephson junction. It's a simple-looking device, just two layers of superconducting material separated by an ultra-thin insulating barrier. But it does something extraordinary. Even though it looks like a break in the circuit, it allows quantum tunneling. Electrons can literally tunnel through the barrier without passing through it in the classical sense. And this behavior introduces the crucial nonlinearity needed to separate the energy levels unevenly, making them individually addressable. This is the strange tech from the quantum realm. A computer made not of logic gates and transistors, but of superconducting circuits, microwave photons, and quantum states so delicate they vanish if you breathe too hard near them. And it's not just computing. The same principles that make qubits possible are opening doors in other directions too. Quantum communication, quantum sensing, quantum simulation. Each of these fields is tapping into the inherent weirdness of quantum mechanics to build tools that would have seemed impossible even a decade ago. But make no mistake, this is not a polished product ready for the masses. We are still in the dawn of the quantum age. Today's quantum computers are noisy, error-prone, and require elaborate infrastructure to function. But the breakthroughs are coming faster and faster. As researchers refine the architecture, develop better error correction techniques, and scale up the number of qubits, the horizon keeps shifting. And behind all of this lies the most haunting implication of quantum technology, that reality itself is programmable, provided you know the language. And that language doesn't sound like anything we've used before. It sounds like entanglement, superposition, and tunneling. It sounds like the whisper of particles that don't obey the rules. We are standing at the threshold of a new technological paradigm, one where the boundaries between physics and engineering, between matter and information, start to blur. It's a strange place. But then again, all revolutions begin with a kind of strangeness. The quantum realm is no exception. To even begin building a machine that manipulates quantum phenomena, you first have to embrace a deeply counterintuitive truth, that particles don't exist in fixed states until you observe them. Instead, they occupy a cloud of probabilities, a superposition of all possible realities that only collapses when an active measurement forces a decision. In practical terms, that means the mere act of observing a qubit can destroy the very state you're trying to exploit. It's like trying to study a soap bubble by poking it with a knife. You can't just look and expect nothing to change. The quantum world demands delicacy, precision, and a kind of quietness we're not used to engineering on a human scale. And yet somehow scientists are learning how to do just that. Take, for instance, the process of initializing a qubit inside a superconducting quantum processor. These processors live at the core of a quantum computer, nestled inside dilution refrigerators that resemble some futuristic fusion of a deep-sea diving bell and a cryogenic sarcophagus. These devices lower the ambient temperature to around 10 millikelvin, just above absolute zero, where thermal vibrations essentially stop and classical noise becomes negligible. It's not just cold, it's a complete withdrawal from the thermodynamic chaos of the normal world. At this temperature, superconducting materials, like aluminum, stop resisting electrical current. The electrons flow as a single quantum fluid, opening the door to behaviors that only exist in this frozen regime. The qubits themselves are built from circuit components carefully arranged to behave like artificial atoms. They're not physical particles in the traditional sense, but manufactured energy states inside resonant circuits. You begin with a nonlinear oscillator built using a Josephson junction, which warps the energy landscape so that you can selectively excite just the first two levels, labeling them 0 and 1, the quantum equivalents of a classical bits 0 and 1. To do this, scientists use microwave pulses finely tuned to match the resonant frequency of the qubit's transition. If the energy matches exactly, the qubit absorbs the pulse and flips its state. If not, it remains unchanged. The system is exquisitely selective, like ringing a wine glass at its perfect tone without disturbing the one next to it. But con, but controlling a qubit is only part of the problem. Reading it out is even trickier. In classical electronics, reading a signal is simple. You just measure a voltage or current. In quantum systems, however, the state you're reading only exists as long as you don't look too hard. To measure a qubit, you have to bounce a microwave signal off a cavity the qubit is coupled to, and then analyze how the signal's phase has changed. The response contains subtle clues, quantum fingerprints, that tell you whether the qubit was in state 0 or 1. This is not a direct measurement. It's an inference drawn from probabilities, reconstructed by sensitive amplifiers that operate near the limits of physical possibility. To amplify these tiny, fragile signals without drowning them in noise, scientists use quantum-limited amplifiers, devices like Josephson parametric amplifiers that boost a signal while adding the minimum amount of noise allowed by the Heisenberg uncertainty principle. These amplifiers are often followed by isolators, which allow signals to exit but prevent unwanted reflections or noise from traveling backward and interfering with the fragile quantum operations. And all of this hardware must be meticulously shielded from external interference. Magnetic fields, vibrations, stray light, even cosmic rays. Any disturbance can cause decoherence, a breakdown of the quantum state that erases information and ruins computations. In essence, every quantum computer is engaged in a constant war against the environment. Despite this complexity, quantum engineers have managed to build working systems, machines with 5, 27, 127, even more than 400 qubits, depending on the design. These machines can perform basic quantum algorithms, demonstrate quantum supremacy on specific tasks, and even simulate small molecules and physical systems that are intractable for classical computers. But they're still fragile, error-prone, and deeply limited in what they can achieve. The real breakthroughs will come when we master quantum error correction, a scheme that uses multiple physical qubits to encode a single logical qubit that can withstand errors from decoherence and gate imperfections. The leading candidate is the surface code, which uses a lattice of qubits and a series of stabilizer measurements to detect and correct errors without collapsing the quantum information itself. It's a mind-bending process, correcting something without actually knowing what it is, but it works, at least in theory. In practice, we're still scaling up to the point where logical qubits become viable. And yet, for all this complexity, quantum computing is just one thread in the broader tapestry of quantum technology. There are other strange devices being built, strange in function, stranger still in implication. Consider quantum sensors, for example. These instruments exploit entanglement and quantum superposition not to compute, but to measure the world with unprecedented accuracy. Quantum sensors can detect changes in gravity, time, and electromagnetic fields at levels so fine they can pick up signals from underground tunnels, monitor brain activity without direct contact, or measure the passage of time to a degree that challenges the very definition of a second. Atomic clocks, which already use quantum transitions to define time, are being refined into optical lattice clocks that could lose just 1 second over the entire age of the universe. Then there's quantum communication, an area of research that sounds like science fiction, but is already producing real-world systems. By entangling particles and transmitting one half across a communication channel, it becomes possible to send information in a way that reveals any attempt at interception. This is the principle behind quantum key distribution, QKD, a technique that uses the laws of physics, not mathematical complexity, to ensure absolute security. If someone tries to intercept the key, the act of measurement collapses the entangled state, alerting the sender and receiver that the transmission has been compromised. This is not just a theoretical curiosity. Governments and private companies are actively deploying QKD systems, and countries like China have already launched quantum satellites capable of distributing entangled photons over thousands of kilometers. All of this, computing, sensing, communication, comes from the same root, the quantum realm, a place that doesn't behave like anything we see or touch, yet underpins everything we are. The strangeness isn't just academic, it's functional, it's useful, and it's giving rise to a whole new generation of technologies that don't just improve on existing systems, they invent entirely new ones. But as we build further into this realm, the philosophical implications start to surface. What does it mean that particles can be connected across space and time? What does it say about reality when observation becomes an act of creation? Are we discovering something fundamental? Or are we just learning new ways to interpret the fog of probability that defines our universe? These questions aren't abstract anymore. They're built into the devices we're constructing. Every time a quantum processor executes a gate operation, every time an entangled photon travels down a fiber optic line, we're testing the very limits of what reality can be. And we're doing it not in thought experiments or chalkboard diagrams, but in hardware. As with any revolution, the early stages are chaotic and uncertain. The devices are temperamental, the results sometimes inconsistent, the promise still distant. But the direction is clear. The boundary between what is physically possible and what is technologically achievable is dissolving. And the closer we get to mastering quantum systems, the more it begins to feel like the rules of the universe are tools we can learn to wield, not just observe. The human journey into the quantum realm isn't just about machines or science. It's about crossing a psychological boundary. For most of history, we've believed the world around us was objective, solid, and deterministic. You drop an apple, it falls. You heat metal, it glows. The universe in this view is like a vast mechanical clock, understandable, predictable, obeying laws as rigid as they are universal. But the moment we pierced the boundary into the quantum world, those beliefs began to dissolve. And the deeper we venture, the more we're forced to accept that reality is less like a machine and more like a riddle. A riddle whose clues flicker between existence and non-existence, whose answers can only be approached probabilistically, and whose logic seems less like law and more like possibility. And yet somehow this riddle is yielding to engineering. At research institutions around the world, teams are creating devices that stretch the very definition of technology. In Austria, they've levitated tiny diamonds using lasers in vacuum chambers, then entangled the quantum spins of the nitrogen atoms within. In Canada, researchers are building photon-based quantum processors that don't use superconductors at all, just light particles bouncing through nanoscopic circuits etched onto glass. In Japan, scientists are exploring topological qubits, strange constructs that could theoretically store information, not in the state of a particle, but in the shape of its quantum field, like tying a knot into the very fabric of existence. These are not just new machines, they are new metaphors. Each one redefines how we think about matter, energy, and computation. One of the most exotic ideas gaining traction is quantum teleportation. No, this isn't the science fiction trope of beaming people across galaxies. In the quantum realm, teleportation refers to the ability to transfer the state of a qubit from one location to another without physically moving the qubit itself. It works through a blend of entanglement and classical communication. Imagine Alice and Bob, each with one half of an entangled qubit pair. Alice also has a third qubit whose state she wants to teleport. She performs a joint measurement on her two qubits and sends the result to Bob via classical means, like a regular internet connection. Upon receiving it, Bob can apply a corresponding operation to his qubit and instantly recreate the original state. The information is not copied, it's destroyed in one place and reconstituted in another. This process obeys all physical laws and has been demonstrated many times. In fact, quantum teleportation is a foundational building block for future quantum networks, a kind of quantum internet, where information exists not in packets but in entangled wave functions. And such a network is no longer hypothetical. China has already launched quantum satellites that distribute entangled photons to ground stations thousands of kilometers apart. This quantum link allows for secure communication, impervious to eavesdropping. In the Netherlands, a team recently demonstrated a rudimentary quantum network between three nodes, each node with its own quantum processor and the ability to share entanglement with its neighbors. As these technologies scale, we inch closer to a world where information is no longer transmitted in bits, but woven into a quantum fabric that stretches across the planet. Imagine a future where your device doesn't download data from a server, but entangles with it, drawing knowledge as though through a shared memory. It sounds fantastical, yet the physics is sound. What remains is the engineering and time. But what happens when this quantum technology starts influencing daily life? One area already seeing ripples is medicine. Quantum sensors are being developed to map brain activity in unprecedented detail. Unlike current techniques, which require massive, expensive MRI machines or invasive probes, quantum sensors can measure magnetic fields at the femtosecond scale, allowing for real-time, high-resolution brain imaging through a simple wearable device. Quantum dots, nanocrystals that emit light in discrete wavelengths, are revolutionizing imaging and targeted drug delivery, lighting up cancer cells with pinpoint accuracy and allowing drugs to be released at specific locations within the body. Even the pharmaceutical industry is preparing for disruption. Quantum computers could soon simulate molecular interactions that are too complex for classical systems to model, vastly accelerating drug discovery and enabling treatments for diseases we currently consider incurable. In energy, the implications are equally staggering. Quantum simulations are being used to understand high-temperature superconductivity, materials that could one day carry electricity with zero resistance at room temperature. If cracked, this would revolutionize power grids, eliminate energy loss, and usher in a new era of efficiency. Quantum research is also exploring novel solar materials that could harvest light with near-perfect efficiency using exotic excitonic states. Quasi-particles formed when light and matter couple inside specially designed nanostructures. In finance, companies are already exploring quantum algorithms that could analyze market behaviors, predict patterns, and optimize portfolios beyond the reach of classical computation. Cryptography, too, is being turned on its head. The very codes that protect our bank accounts, military secrets, and national infrastructures rely on problems that classical computers find hard to solve, like factoring massive prime numbers. But quantum computers, through Shor's algorithm, could solve these problems exponentially faster. When large-scale quantum machines become practical, much of today's encryption will become obsolete overnight. That's why governments are racing to develop post-quantum cryptography, systems that remain secure even in a quantum future. But there's another layer to all this, one not often discussed: the philosophical and psychological transformation quantum tech demands of us. When we build machines that rely on uncertainty, when we transmit information through entanglement, when we teleport quantum states across the globe, we're not just changing how we compute, we're redefining what it means to know. In the quantum realm, certainty dissolves. Knowledge becomes relational. Observation becomes participation. The boundary between subject and object blurs. And in building tools that operate in this domain, we are, in a way, integrating that uncertainty into the core of human activity. There is something deeply humbling in this, that beneath our rigid categories, our laws, our symbols of control, lies a reality that defies classical logic, that flows like a river between potentials, that does not ask for our permission to be strange. And yet, paradoxically, we are now mastering this strangeness, not taming it, but collaborating with it. Every superconducting chip, every microwave pulse, every cooled cavity and entangled photon is a small pact between humanity and the unknowable, a handshake between our desire for order and the cosmos's insistence on ambiguity. Where this leads is impossible to say with certainty. Quantum technology is still in its infancy. Most of its applications are years or decades away from becoming mainstream. But the foundations are solid, the experiments are reproducible, the math is unforgiving, and the trajectory is unmistakable. We are entering a time when the boundaries between the physical and the informational, the real and the potential, will blur. And in that space, new tools, new ideas, and new paradigms will emerge, born not from silicon, but from the deepest riddles of the universe. What's most exciting is that we are only scratching the surface. We've mastered a few atoms, we've controlled a few photons, but the quantum world is vast and untapped. Hidden within it could be architectures and principles so alien that our current technology would seem primitive by comparison. Just as the transistor once transformed society, so too might quantum logic reshape everything from science to culture to consciousness. It's a kind of awakening of physics, of technology, and perhaps of ourselves. In the end, strange tech from the quantum realm is not just about the gadgets we build. It's about a shift in perspective, a new lens through which we view reality, one that embraces paradox, celebrates uncertainty, and invites us to think, not just deeper, but differently. And as we step further into this realm, guided by supercooled circuits, entangled particles, and whispering microwaves, we may find that the strangest technology of all isn't the quantum computer or the teleportation circuit or the entangled satellite, but the human mind itself, reaching beyond the classical into the unknown.